All right, let's pick up where we left off yesterday, where I had a complete brain malfunction. Thankfully, Alex was there to correct me at the end, but not soon enough that...
Bradley first. I think Bradley
Oh, okay.
Bradley's not here, so you get...
Okay, good. There you go. You could take credit. And by the way, I'm going to show a clip from a video today. I've linked the video on my Canvas page for today. It's an entire lecture on capacitance from Walter Lewin, who, if I was you guys, I would watch and treat it like a class over the summer. His Physics 801 and Physics 802. The entire lecture course is on YouTube. Any future physicist, chemist, engineer probably going to have to take those classes in college. Definitely engineering, most definitely electrical engineering, most definitely physics majors, some chemistry majors at some schools don't have to take second semester calculus-based physics, but Walter Lewin's regarded as the best physics teacher, one of the best, if not the best of all time.
Second to you.
Second to me, of course.
I'm going to major.
Flattery will get you everywhere. It is MIT. He's retired now, but he was MIT, so it's an MIT level course. If you notice, when you watch him, a lot of what he talks about we cover in this class. The assignments given and tests given in that class are obviously going to be significantly more difficult than they would be in this class because it is MIT. And yeah, they hold those kids to kind of a high standard. Yes, sir?
I'm majoring in biochemistry, and the course, she has two physics classes, calculus-based physics. And
Okay.
I asked them about this one, if I pass the test, if it would cover, and they're different, like, course numbers, and she said she'd have to look and see if they would, like, accept this class
Okay.
place. So I might have to take more physics.
Yeah, you might have to.
You might not be the best physics teacher.
Probably not. Okay. Based on yesterday's performance. So anyway, I bring that up because on that same lecture, because we don't really have time because it takes kind of a while to talk about where this came from, but he goes through where that integral that I showed yesterday where you had to integrate over the volume to generate this equation. He goes over that in that video, so if you really want to get that. And then he goes over in that 802 a lot of stuff that we don't get into, a lot of stuff involving electromagnetic radiation and light and stuff like that. So it would behoove you. It's interesting too. So anyway, we have this equation, and then we have two expressions for the electric field. We have the magnitude of the electric field I could write as the potential difference divided by the distance, and that comes from what we talked about yesterday. The potential difference is equal to the negative electric field times distance, plate distance when we're talking a parallel plate capacitor. And then we've all known for a while now that the electric field is sigma over epsilon naught for a parallel plate, for two parallel plates oppositely charged. The volume in this region is the area, surface area of the plates times the distance separating them. And then the charge density is Q over A, charge per unit area, which we can then write as area equals charge divided by charge density. Keep in mind that yesterday we talked about a plate, the two plates that were already separated, and then we separated them more. But imagine if they were touching, but not like in direct contact so you can have charge go from one to the other. But say they were infinitesimally close together, but charge couldn't flow from one to the other. And then we separated it. Then we generate electric fields essentially from scratch, right? We generate electric fields by doing work. And by doing work, we then store energy in that electric field. In this case, we have a capacitor. So the symbol is a U for energy. U is a general term for energy, sometimes V, but most of the time U, and with a subscript C. And that tells us that's the energy stored in the capacitor. And you've seen energy stored in the capacitor. I did the jar thing in here, right? So you've obviously seen the energy stored in a capacitor, and then I charged the thing and lit the light bulb with it, so you saw it that way as well. Well, that uses this energy here, which I can then take this equation and make these substitutions. And yes, I'm going to substitute the two different electric field equations in for each electric field because the electric field gets squared here, and you'll see why I do that because I want a nice equation. Easily used equation that gives us the energy stored in a capacitor. So when I make those substitutions, the energy stored in the capacitor will be 1/2 permittivity of free space, epsilon naught, times the first electric field, which I'll put potential difference over plate separation, times the second electric field, which I'll put charge density over epsilon naught, times the volume. Well, the volume is the area times the distance, right? But the area I can write as charge divided by charge density, right? So instead of having the area there, I can write the charge, total charge on the capacitor divided by the charge density, and then times the plate separation. There's a point to all this, I promise. Because look at all the cancellations. The plate separation cancels, charge density cancels, permittivity of free space cancels, and I'm left with a nice, succinct equation. The energy stored in a capacitor, parallel plate. This is specifically a parallel plate capacitor. I know that because sigma over epsilon naught is the electric field that exists within a parallel plate capacitor. Remember, it's sigma over 2 epsilon naught, the electric field due to a large charge sheet. When I have 2 of them with opposite charge, then I double that electric field, so it's sigma over epsilon naught. So that'll be 1/2 times the charge Q times the potential difference between the plates, delta V. So that's a nice, easy equation. Back in the day with AP Physics B or in AP Physics 2, which we don't teach at this school, this is the equation for the energy stored in a capacitor that you're just given. Okay, and we've kind of derived it. We didn't go from scratch from the beginning, but again, if you watch that video from Walter Lewin, from start to finish, you'll see the whole derivation. Now, this isn't the whole story. On the formula sheet, it's written slightly differently. You have this to start with, but then it also says equals 1/2 capital C times the potential difference squared. This is what is on the formula sheet. It's written like this. The energy stored in a capacitor is given on your formula sheet like this. So that's on the formula sheet. So there's something here that we haven't seen before. One of these things. The C, capital C. Capital C is the capacitance. And so the capacitance is a thing that is calculable and measurable, and there are equations with it. But before we can understand what it actually means, let's just talk about how it's defined. The capacitance C is simply defined as, in words, and is defined as, is the 3 horizontal lines. Capacitance is defined as the amount of charge you can store on a conductor per unit of electric potential. Potential difference. What's that? Not times, per. Q over delta V. So capacitance, the equation is just total charge over potential difference. What does that mean? That means how much charge. It tells you how much charge you can store on, say, a conductor like the Van der Graaf generator per volt of electric potential. So right now you can't really store much charge on it. You can, but not really. If you start storing charge on it, you're actually going to build up electric potential, right? The electric potential difference between this sphere and infinity, or significantly far away. So you can change the amount of charge that's stored by changing the electrical potential difference, right? But they're going to change in relation to each other such that you're going to get the same value for C. So the capacitance of this capacitor is the same regardless of whether it's charged or not. If I start discharging the capacitor, well, then the potential difference between the capacitor plates goes down, and they go down at the same rate, so that this ratio always gives me the same value. Okay. So the capacitance on a capacitor doesn't change whether it's charged or not. Okay, so if we understand that, it's charge divided by potential difference. The units are coulombs per volt. And unfortunately, potential difference, the symbol is V, the unit is the volt, which has the abbreviation capital V. So if I had a voltage of 10 volts, it would be V equals 10 V. So it is kind of annoying that they picked the same thing for the unit that they did for the symbol in the equations. Usually they don't do that, but they did that for the volt. So the units for capacitance are coulombs per volt, which...
Isn't that called something?
Yeah, it's called something.
Farad?
Farad, yeah. Which is a capital F. Named after a guy named Faraday. Why they didn't call him Faradays, I don't know. They call him Farads. Yeah, Alexander or Alessandro Volta.
So Coulomb, right?
Yep.
John D. Coulomb.
James J. Coulomb. John D. Coulomb.
Wow.
John Smith Coulomb.
That's where they got grams from you.
Yeah, exactly.
They just took up some letters.
Yeah. Was there a guy named Ampere?
Yeah.
So they're all named after
John D. Ampere.
Now this is a Leyden jar. It's named after a place called Leyden. There's another famous physics teacher named Paul Hewitt, who interesting story. We got some videos from him, but he's kind of outdated now. He's real old now. But he would make jokes when he was teaching. He's like, Ampere's law, named after Mr. Law. Anyway, that's an aside. So yes, capacitance units are farads. And it's just a measure of how much storage or how much charge storage you can have per volt. Okay. And we can change the capacitance by changing various aspects of our capacitor. And in general, capacitors that are actually useful are parallel plate capacitors, even if they look like cylinders. This is a parallel plate capacitor. It's just been rolled up. You got the two plates that are malleable, separated by usually a piece of thin paper or some kind of thin insulating material, and then they just roll them up and stick them in a tube. There are some things called cylindrical capacitors, which is like just a cylindrical conductor surrounded by a cylindrical conducting shell, or spherical capacitors, which is just a spherical conductor surrounded by a spherical conducting shell, and then they're charged to opposite polarities, right? One's positive, one's negative, and both of those. In reality, those are not useful at all. You never find any device that has those in them. They're used purely for just demonstration, understanding purposes, the understanding at the basic level. But in practice, really all you see are parallel plate capacitors. Okay, as far as I know.
What material is it made out of?
It's usually metal, like aluminum or copper. Yeah. I'll tear one of these. I'll tear one of the capacitors open maybe tomorrow, and we can look at it. Yeah, that because those are semiconductors. Silicon's a semiconductor, and so it's used in circuit boards for all the on and off switches, right? Diodes are like valves. They're like they allow electricity to only flow one way. Okay, so I brought up the spherical and cylindrical conductors or capacitors because that's usually what you start with when you're talking about determining the capacitance or mathematically dealing with the capacitance. We're going to start with a spherical capacitor or a charged spherical conductor, and then we're going to show why they're so impractical. So say we charge the Van de Graaff generator. And note that the Van de Graaff, I'm not frightened at all about charging that to its maximum capacity. And think capacitance, right? It's the capacity to store charge. Its maximum capacity, and then putting my hand next to it and getting shocked. I have no problem with that. Some people do. It really doesn't hurt. It's more just like shocking than anything.
That's the guy who blacked out.
No, not from that. From this, I definitely am terrified of charging this up. Even when it's uncharged, I still am hesitating. Like, yeah, no, this guy stores way more charge. It has way more capacitance than that guy does. And it's because it's got the insulator and it's got two metal plates that then develop opposite polarities. When we just store charge on that spherical capacitor, then the potential difference we're dealing with is not a large potential difference between two plates, because one's positive, one's negative, and they're real close together. We're talking about the potential difference between the surface of the potential at the surface of the Van de Graaff and the potential at infinity, located quite a distance away, right? And as we'll see, the capacitance there is very, very small. So let's just talk about and show why spherical capacitors are pretty useless. We can increase the capacitance by surrounding the Van de Graaff with another charged shell, so the distance between them isn't very big, and it has an opposite polarity charge, but it's still not going to be nearly as much as a parallel plate capacitor. So let's talk about the capacitance of a charged spherical conductor. So, and since we have the Van de Graaff generator, pretend this is the Van de Graaff generator dome. And we're going to charge it to charge Q. It's going to have a radius R. And so the electric potential at the surface, meaning the electric potential an infinitesimal distance above the surface, right? So right above the surface, the electric potential is going to be K, or 1 over 4 pi epsilon naught, times Q over R. I know at least Mr. Nelson remembers that, based on the silly remind message.
That was me.
It made me laugh. What was that?
That was me. What are you talking?
It's not you.
Apparently at one point you sent a remind message intended for us to the Physics 1 students.
Yeah, they told me that after the fact.
Cast or something.
Sorry about that. I wasn't going to bring that up, though. Okay, so we have an expression for the electric potential at the surface of this guy. It's just KQ over R, right? Right off the surface, it acts like a point charge. But if this acted like a point charge at the center here, then at the surface we would be a distance R away from it. And using our new equation for capacitance, which is real simple, it's just Q over delta V. And remember, delta V, if we're referencing it to infinity, is just V at that location, right? Because the potential at infinity is just 0, right? And so all I have to do is divide the charge Q by this expression, which means flip the guy and multiply, right? Because I'm dividing by a fraction. So I'm just going to multiply that by 4 pi epsilon naught times R divided by the charge Q. Q's cancel out. It gives me a capacitance of 4 pi epsilon naught times the radius, R. What does the capacitance of this capacitor depend on? The radius.
So it doesn't matter how much you charge it, it's not going to change.
Yeah. Dependent on radius only. So remember, the capacitance doesn't tell you how much charge is on the capacitor. It tells you how much charge you can put on the capacitor. Okay? It's a measure of the capacity for the thing to store charge, whether it's charged or not.
And that's tiny too.
And that's very tiny. Very tiny. And capacitance is usually pretty tiny. A capacitor with a 1 farad capacitor can store a huge amount of charge, actually. So, but this is exceedingly tiny because epsilon naught is 8.85 times 10 to the negative 12, right? And then the radius here for that guy is about 15 centimeters, so it's 0.15 meters. And so yeah, if you want a useful capacitor, this guy right here is 30 microfarads. So that's 30 times 10 to the negative 6 farads. This little one here is 1,000 microfarads, so that's actually quite a bit more than this guy. 1,000 microfarads.
And how come why not just say like 1?
Because it was based on the Coulomb, and the Coulomb, because it's such a large amount of charge, it makes the capacity to store that charge, the value's typically pretty small.
I'm just saying specifically for that
Because you get microfarad is used, micro and nano coulombs and micro and nanofarads are used quite a bit, and so I think it's for electrical engineering, just to make electrical engineering easier. Everything in microfarads, right? So I don't know. I'm not honestly that sure, but that would be my guess.
It's like you so couldn't just do like one property or something.
Yeah, it's 1,000 microfarads, so it would be 1 millifarad. Right? Yeah. Okay, so what if we wanted to store 1 coulomb of charge per volt? And so this is an interesting question. I'm going to erase it this side.
What can store it on a charge?
There are capacitors that can do that, and depending on what type of insulator you put between them, they can be dangerous or they might not be dangerous. Some capacitors can hold a lot of charge, but they discharge and charge very slowly. When this guy gets charged up, it gets discharged very quickly whenever I just tap it, right? But then if I tap it again, you'll see another spark. And if I tap it again, you'll see another spark. And that's because it doesn't discharge all at once. So this capacitor discharges very quickly. Some capacitors take quite a bit of time to discharge, depending on how they're actually constructed. And we'll definitely get into that when we study circuits, resistor, capacitor circuits. Good question, though. So yeah, just because you can store a coulomb of charge per volt on a capacitor doesn't mean it's explicitly dangerous. It can definitely be, but it doesn't mean it definitely will be. All right, so how big? Let's say I have a Van de Graaff generator, and I want to know how big R needs to be to store to have a capacitance of 1 farad, to have the ability to store 1 coulomb of charge for every volt of potential on the surface. And so I'll phrase it like this. How big must R be if a spherical capacitor were to store 1 coulomb of charge, install charge, per volt of potential. Meaning, I want a 1 farad capacitor. And let me actually, I think here, maybe they're here. I have some 1 farad capacitors. I'll try to find them. I have some 1 farad capacitors. They're actually not that big. They're smaller than this guy. So I can hold a 1 farad capacitor in my hand. Let's see how big R needs to be in order to a Van de Graaff generator to be able to have the same type of storage capacity. So if we know the capacitance is simply 4 pi epsilon naught times R, well then R is just going to be the capacitance divided by 4 pi epsilon naught. Or as you notice, just Coulomb's constant times the capacitance. The capacitance we want to be 1 farad, and so it's just going to be 1 divided by 4 pi times 8.85 times 10 to the negative 12. And this is all SI units, so our answer is going to be in meters.
Is it just going to be K?
It's going to be, yeah, duh. So it's going to be 8.99 or 9 times 10 to the 9th meters. Just to put that number into perspective, the radius of the Earth was about 6,000, it's like 6,500 miles or something like that. Isn't it?
How do I measure?
So that's the radius of the Earth. This is about 5.5 million miles.
What's that?
So if you wanted a Van de Graaff generator to have the same capacitance, ability to store charge per unit of electric potential, obviously the amount of charge that can be stored will be different, but you want to have it at the same electric potential. You'd have to have the Van de Graaff about the radius of the Van de Graaff be about 5.5 million miles.
Yeah, I was gonna say, like, if you're to make a shell around the sun that is that size, how far away would that actually be?
Well, the sun is 93 million miles from the Earth, I think. So it wouldn't reach the sun, for sure.
No, I'm saying, like, if
that's
you were to
so
make a
bigger than the
shell
sun.
just around the sun, how far would it reach out?
Pretty far. I think the sun's like 800,000 miles across
Yeah,
diameter.
the sun's radius is 432,600
The Dyson
miles.
sphere is also storage torque.
Yeah,
Okay,
Dyson sphere.
So,
Hmm?
that distance is it's longer than even the distance from the sun to Jupiter.
No, it's not. No.
Yeah.
The sun to Earth is
Meters are 50
Yeah,
kilometers.
9 times 10 to the 9th meters?
Yeah, the distance is between the sun and Jupiter is only 760 billion meters, which would be
This is 9 billion.
Oh wait, yeah,
Meters.
that's right.
Yeah.
Never mind.
I was like, unless I didn't make my notes wrong.
No, only 760 billion.
That's 9 million.
So, anyway,
That's like more money than Monster Musa had.
this guy's about 1,000 microfarads, and I just did the calculation. I think I got this from Walter Lewin, his lecture. A 700 microfarad capacitor, so that's like a little less than this. A 700 microfarad capacitor, spherical capacitor, which again I'm referencing the potential difference to infinity, not to anything surrounding it. We'll talk about that later. You'd have to have a spherical capacitor Van de Graaff generator about the size of the Earth. If you wanted 1 picofarad, then you would want. Then that's when you'd get in the realm of normal size, and pico is like times 10 to the negative 12. No, that's 12th, I think. Yeah, so it's ridiculously small. Notice then that you're talking about 10 to the negative 12th divided by 10 to the negative 12th. Now you're getting numbers that actually make sense. So bottom line, a single charged sphere can store charge on it, but not a lot. Which is why I am not terrified at all about charging up the Van de Graaff generator and sticking my hand on it, right? Or insulating myself, putting my hand on it, and then fist bumping you guys. Although, with COVID, I don't know if we're allowed to do that.
It'll just kill the COVID with his app.
How big of a sphere would you need to compete with the jar?
I'm not really sure. I don't know what the capacitance on this guy is. Maybe I should look that up.
Should do a physical experiment.
Okay. Now what I can do, when I charge the Van de Graaff generator up, am I still recording? I hope this is saving.
No.
I don't know what I'm going to do. I really needed that last lecture.
Just make it record
Dan
24/7.
Fullerton.
Just make it record 24/7.
I'm going to run out of space.
In case someone tries to just live here and steal physics.
Yeah. What about behind the cat, you know?
I'm taking your physics. Just grab the jar. It's 13 microfarads.
Okay.
Or we could. What's that movie
Just
called?
wait there. Let me source this up real quick and then you're gonna hold it.
Mr. Graham, what's that movie called with the janitor was a genius?
Genius.
Good Will Hunting?
Yes. Yeah. We could have one of those situations. We'll have proof.
That was like Matt Damon's breakup before.
So, time travel or something? Well, time travel to the future is possible.
Yeah.
Past.
Calculate the voltage based on knowing the conductivity of air.
Wait, say again?
Could you calculate the voltage based on knowing how conductive the air is and how far away the spark is?
Yeah.
Okay.
We'll talk about that a little bit, but not so much. But yeah, for sure.
And if you know the voltage, then that helps calculate capacitance.
You need to know.
Right. But like, if you were to design an experiment to calculate the capacitance of that jar, would that be a way to do it?
Yeah. We'd have to measure that potential difference, which we'd be able to. We probably could.
But no labs this year.
I think our voltmeters are a little sensitive. The ones that we have here are probably a little too sensitive. They'd probably just break. Because voltmeters, you don't want them to actually be part of the circuit. Because if they're part of the circuit, then they're going to discharge, right, the circuit. And so they act as resistors with 100% resistance. You want them to, but I feel like the charge on that is so much that it'd probably just break right through and break the voltmeters. But we can try because I got a ton of them, so we can break one. I'm just gonna let you do it because I don't want to be touching those wires. Okay. Play the stupid microphone.
So can you approximate, like, based on how far the charge is in the air?
Yeah. If you knew the conductivity of the air. Yeah. Okay. So I can, and this is to show you why, if you want a capacitor the idea is not just to be able to store charge. The idea is to be able to store charge in the appropriate amount for what you want to do, and to have it discharge and charge at the rate that you want it to do so. And there's ways that we can control that. Okay, if you just charge a sphere with the belt, that's going to build up the maximum amount of charge. There's really nothing else you can do, right? But what we can do, and notice that when you change the capacitance, you change the electric potential. If I have the same amount of charge on this, let's say I charge it to the maximum amount, but then I don't do anything to it, so I'm not discharging or recharging it, and then I want to change the capacitance, I have to change the electric potential difference, right? And so I can actually do that. I can do that by, and let me just generate the electric field real quick.
Wow.
Impressive, right? And I'll know there's an electric field here. I know that it's generating an electric potential because I got the little pith ball. Okay. So I know that I can change the electric field here. And watch what happens. If I just bring this other guy closer, it moves, and then it moves back whenever I move this farther away. The closer I move this other guy, and this guy's neutral. This guy, I'm not getting shocked. This guy would get shocked if I touched it. The closer I get, the smaller the electric field becomes, right? And hopefully you can kind of understand why. This guy's positively charged, which means when I move this guy close, the negative charges on this side migrate to this side. Now I have kind of a capacitor configuration. I got a positive charge and negative charge on this side of the dome, right? Creating electric field between them. But the overall electric field is actually going to be reduced, right? Because now remember, electric field is like force per unit of charge, right? Well, if I have it there, then the force per unit of charge, the force is going to, look, I can change it too. Oh, that's funny. And it's because of that whole charge polarization idea, right? And so I can change the capacitance of this spherical capacitor setup by having another sphere that is overall neutral, but that will have charge polarization in it. Remember, that's why the balloon sticks to the wall. That's why Connor's head sticks to the wall.
Yeah.
And I can change how that charge behaves by just changing the separation between them, right? Notice that this guy picked up a positive charge from the dome here because it was in contact when I charged it. And so as I move this guy closer, he actually feels a force that points towards this guy as well as a repulsive force from there. And so I just want to talk about that as a starting point now, and then you discharge it and it just falls immediately. So and we'll expand if that's a little, if what I was trying to get at there was a little mysterious, it'll become clear hopefully in the next few minutes. So let's talk about what just happened. I charged one.
You should move the camera.
What's that?
You should move the camera.
I don't have to. I can't the online students do it themselves.
Just get up and move it. It's that hard.
I'm not saying I don't understand why, but I can't wait till school's back to normal. Last period, the whole video, all period. I really needed that. 0 bytes. I'm looking at it right now. 0 bytes.
You're fishing?
What's that?
You're fishing?
Get out, Mike. Get out. Get out. Okay, turn the camera. Okay, where was? All right, so let's talk about the situation I was just kind of showing. Let's say I have sphere A, and sphere A, let's say, was a negative charge. I built up negative charge on it. And I'm only going to focus on the right side because I'm going to bring sphere B in. And sphere B, the negative charges on this side get repelled from there, and if these are conducting spheres, then they just move to the other side, building up a net positive charge. Right? Now it's not a parallel plate capacitor, obviously, but it's now starting to kind of look like one. Right? And a parallel plate capacitor, by the way, well, no, I'll get to that in a few minutes if we have time. Now the capacitance here is actually going to change. So if I had the capacitance just due to sphere A, due to the potential difference between the surface of sphere A and infinity, but then I bring in sphere B, I'm actually going to change the capacitance. And I want you to understand why. Okay, so let's just say a point here. Let's pick a point, a random point right there. The electric potential at that point, so I'll call that P. The electric potential at point P is going to be the amount of work required to move charge there per unit of charge, right? The work, and work is Q times V, or the electric potential is just defined as electric potential energy per unit charge. Well, the electric potential energy is exactly equal to the amount of work that you have to do to get the charge there. If sphere A wasn't here, and our charge that we want to move in is positive, it's harder to get that charge to point P. If I have this negative charge here, it's actually easier now because I get an attractive force from this guy while I get a repulsive force from this guy. So the work required to get a charge to point P there is actually going to be a lot less. And so I'm going to get a much smaller potential there, right? I move sphere A away, and the potential here goes up, okay? So what happens whenever I bring these two guys close together, I'm not referencing the potential difference to infinity anymore. I'm actually getting a smaller potential difference between the two sides. And if just, I feel like it's hard to understand that mathematically. I think of the work required to move a charge in, right? Without sphere A here, to move a positive charge to this point P requires a ton of work, requires a lot of work. If charge A is now brought in, or sphere A is brought in, and it's negatively charged, it actually requires a lot less work to get that object to point P. Does that make sense? Which means the electric potential at point P has gone down. Which means the electric potential at every point in space around here, of surrounding sphere B, has gone down. Which means my overall electric potential has gone down, which tells me that the capacitance of this system of charged spheres has also gone down as related to how much capacitance sphere B had all by itself. Because capacitance is total charge divided by the potential difference. Well, now the capacitance, the amount of charge didn't change, right? If I charge B to a certain positive charge and then bring sphere A in proximity, the amount of charge on sphere B did not change. And so the Q doesn't change, but the electric potential will go down, potential difference will go down, which will increase the capacitance. So just by bringing in an oppositely charged object into the system, I've increased the capacitance by decreasing the potential difference. Okay, does that make sense? It's just one of the things that the equation tells you. The equation for capacitance tells you. Right?
So the potential difference would go down whenever you have two spheres because there's an attractive force from the positive charge to A.
Yeah.
Yeah.
To a potential positive, like a test charge. Yeah. Mm-hmm. Without this guy here, it'd be a lot harder to move a positive charge to this point. And the same thing, it would take actually negative work to get it to closer to this guy than that guy, because you'd have to be pulling away from it in order to let it come to a stop there. Yeah. And so the potential difference, the potential of the whole system goes down. The potential difference between these 2 points is going to be less than the potential difference between the surface of this guy with A naught here and infinity. All right, so that's one way that we can control the capacitance of a capacitor, is just by varying the distance between them. By varying the distance between them, we change the potential difference, and which then increases or decreases the capacitance. All right. In general, though, still you need giant spheres to have any type of significant capacitance. And we don't want giant spheres. We want things that we can roll up into little tubes and put them in circuit boards, right? Some capacitors are even a lot smaller than this guy.
What do you mean you don't want to build a massive Dyson sphere size capacitor?
Well, if we could build a Dyson sphere, that would be... Or you say size can... Okay, yeah. That wouldn't be practical. Wouldn't exactly be practical. Okay.
Get out of the Dyson sphere that's also capacitor.
Yeah? Get on that. Homework assignment. If you can get that done by the end of the year, I will give you an A.
Forget the AP test.
Yeah, yeah. Okay.
All it is one major AP score.
Yeah, we don't need to do anything anymore. We'll have unlimited energy. I think you'd be set for life.
Nah.
But he would have never passed the AP exam.
I'm a failure.
Okay, so I got two capacitor plates, and I'm going to go back down to actual parallel plate capacitors because I want to talk about... God, when I start saying capacitor over and over again, the word sounds really weird coming out of my mouth. Okay, so I have a parallel plate capacitor, and we have our new equation for capacitance, but we want to be careful about something now because when we have Q there in the equation, I have a plus Q up here, and I have negative Q down here. I have a positive charge and a negative charge. If these plates were initially uncharged and I put wires to them on either side and connect them to a battery, naturally they attain the same magnitude of charge. If they didn't, then charge would flow according to Coulomb's law until they did. So what happens is that I have the same charge density on the top, right? It's going to be charge density times area, but it's going to be positive. On the bottom, it's going to be negative charge density times area. But those charge densities will be the same, just one will be positive, one will be negative. And so it would, unless we came up with this convention, lead to confusion. We have this new equation for capacitance. Well, which Q do we use? This one, that one, do we use both? Well, we can't use both because the total charge is just 0, so that wouldn't make sense. So when we have real capacitors, parallel plate capacitors that are actually useful, we actually just say that capacitance C, is the charge on one plate, where the magnitude of the charge on the other plate will be the same, it'll just be negative, divided by the potential difference between the plates. Okay. So we have to be careful about what Q means. Q is really just the charge on one of the plates. Okay, that's how we use the equation for capacitance, just by definition. And by convention, it is always positive. Okay. Sometimes the potential difference will be negative, but you can think of the capacitance as being the magnitude of the ratio of charge to potential difference, even if delta V is negative. Okay. And again, if you hook this up to a circuit and allow charge to flow, you connect it to a power supply or a battery and allow charge to flow, naturally it will develop the same amount of charge on each plate.
And having it always positive makes sense because it'd be the same whether you put positive charges in or electric charges in and negative charges.
Yeah. But again, regardless, if you load this guy with negative charges, then they drive negative charges away from this guy, and you end up with the same positive. And so if you pull negative charges from this guy, then it's going to pull negative charges towards this guy. Right.
One of those things where it's less like a number in of itself, more just like a constant in equations.
Yeah.
Kind of like the spring
Maybe.
Sorta,
Yeah,
Kinda.
kind of.
It's
It's a number that stays the same regardless of what's going on. Yeah.
It's in the same vein of, you know.
And we'll actually see when we get towards the end of the year, we'll see that in certain types of circuits with inductors and capacitors, you can actually have charge flow back and forth. And it'll actually act like a simple harmonic oscillator, just like a mass on a spring. Anyway, real quick, we know that Q, here's our definition of capacitance. We know that Q is sigma times area. I want to get this before the end of the period. We know that the potential difference, the magnitude of potential difference is electric field times parallel, the capacitor spacing, which is this distance. And then I know that electric field is sigma over epsilon naught. So this is going to be sigma A over D times, because I'm going to flip the guy and multiply. So times epsilon naught over sigma. So the charge density goes away. Again, charge doesn't matter when it comes to capacitance. And my result is simply the area times the area, plate area, times epsilon naught divided by the plate spacing. That's the capacitance, an equation for the capacitance for a parallel plate capacitor. Again, lastly, it is dependent only on the geometry of the capacitor. All it depends on is the cross-sectional area, or the area of the plates, and the distance that's separating them. So you can change the capacitance by changing the plate area, or by changing the distance between the plates. Or by inserting a dielectric, which we'll talk about next year sometime.
Permittivity of free space.
Or by changing the permittivity of free space.
Yeah.
Yes. That's also a take-home project for you, Alex. Have a good day. Get out of here.